In this video, we will talk about how to find absolute extreme points of multivariable functions. So we're going to be finding absolute maxes and absolute mins. So the key to finding where these places happen is the following theorem. It says that if f is continuous on a closed and bounded region D, then the function f attains its maximum and minimum values on that region D. So that means somewhere in the region D, f is going to reach a point where it actually hits its maximum value. And there's going to be another point in the region D where f hits its minimum value, where it reaches it. And then also, if the partial derivatives of f exist, then the absolute max and absolute min can occur at one of two places. They can either occur at points where the partials all equal 0, or at least one partial is undefined. So this is just another way of saying that the absolute max or the absolute min could happen at a critical point. Because critical points are places where the partials either all equal 0 or at least one partial derivative is undefined. So it could happen at a place like that, or it could happen at the boundary of this region, at the boundary of the region D. Okay, so before I do an example, I just want to explain what the terms closed and bounded mean. So closed means that the region contains its boundary. And we'll see what this looks like in an example in just a minute. And bounded means that the region does not go off to either positive or negative infinity in any direction. Okay, so let's look at an example of this theorem with a single variable function. So let's say that y was equal to f of x. So I have a single variable function, and I draw my axes. So I have my x-axis and my y-axis. And let's say that my function looks like, starts here at -2, and then it goes upwards, and it reaches a high point here. And then it goes downwards and stops at an endpoint right there. And let's say that this right endpoint happens when x is 4. So based off of this graph, we can see that the domain stretches from where x is -2 to where x is 4. So the domain here is the closed interval from -2 to 4. It includes those endpoints. So this domain is a closed region. It's closed because it contains these endpoints, and the endpoints are the boundary of this interval. Okay, it's also bounded. This is also a bounded region because the domain doesn't go off to infinity on the right-hand side, and it doesn't go off to negative infinity on the left side either. So this is a closed and bounded region. So that theorem says, well, this function is continuous. When it's continuous on a closed bounded region like this, it should reach its absolute max value somewhere, and it should reach its absolute min value somewhere. And looking at this graph, the absolute max happens at this point. So here is where the absolute max occurs. And the absolute min, the lowest it ever gets, happens to be at this right endpoint. This is where the absolute min occurs. So notice that the absolute max happened at a critical point of this function. The derivative is 0 at this sort of peak, at this high point. And the absolute min happened at an endpoint. It happened at one of the boundary points. So that agrees with what the theorem said. All right, so now let's do an example where we find the absolute max and the absolute min of a multivariable function. So this example says, let's find the maximum and minimum values of the function f of x comma y equals 2 plus 3y minus y cubed minus x squared over the region 0 is less than or equal to y is less than or equal to 9 minus x squared. Okay, so the first thing that I want to comment about this is when a problem just says find the max and min values, if it doesn't specify whether it means local ones or absolute ones, it's implied that it's talking about absolute extreme points. So this is asking for the absolute max and the absolute min. Okay, so to get us started, I want to focus on this domain, this region that it's talking about, where 0 is less than or equal to y, is less than or equal to 9 minus x squared, and I want to draw that region. Okay, so I'm going to draw some axes. I'll have my x-axis and my y-axis. So I'm going to focus on the smallest y could be, so y could be equal to 0. That's sort of the smallest it would get. And y equals 0 is just a line on the x-axis. So that's the line y equals 0. And the largest y is allowed to be equal to is y could be equal to, let me put this in a different color, y could also be equal to 9 minus x squared. And that's a downward facing parabola. So 9 minus x squared would look something like this. A downward facing parabola that has vertex at the point 0, 9. And it's not hard at this point for us to find the intersection points, these x-intercepts of the parabola and this line. So one of the intercepts is 3, 0, and the other intercept would be negative 3, 0. Okay, so this is saying that y needs to be greater than or equal to 0, which means we're looking at points that are either on that line or above it, and y needs to be less than or equal to 9 minus x squared. So that means we're looking at points on the parabola or below the parabola. So if I shade in that common region, it's everything sort of enclosed by these two curves. Okay, so everything that's shaded in here constitutes the domain, the region that we're looking at, that we're sort of limiting ourselves to. So the domain is everything that's sort of shaded in this region, as well as this boundary curve. The boundary is included because of these equal signs on these inequalities. All right, so our goal is that we want the max and min values of our function f over the shaded region. That's the domain. We want the max and min values of our function over that domain, the shaded region. So the general strategy for this is we first try to find the critical points. So we are going to find the critical points of f over the domain, So there might be critical points of f that don't lie in this domain. So if there are critical points that don't lie in the domain, we're just going to ignore them, because we just care about what's happening over this specific domain. Okay, so part of what we'll do is we'll find the critical points of our function over the domain. Those are possibilities for where that max or min might happen. And if we refer back to this picture again, so our max, our absolute max and absolute min could happen at a critical point, like it did with this point up at the top. But the absolute max or min could also happen at these boundary points. So with a multivariable function, we're going to have to look at this entire boundary curve and think about what are the possible places that extreme points could happen on that boundary curve. Okay, well let's first find the critical points. Okay, so to find the critical points, let's take partial derivatives. So the partial with respect to x is negative 2x, because 2 is a constant, and then the next two terms only have y as the variable. So when I take the partial with respect to x, the first three derivatives are all 0. So I only end up with the derivative of negative x squared, which is negative 2x. So the partial with respect to y, so the partial of 2 would be 0. The partial of 3y would be 3. The partial of negative y cubed is minus 3y squared. And the partial of negative x squared would be 0 because I'm taking the partial with respect to y, so that means x gets treated as a constant. Okay, so looking at these partials, it's not hard to see that they're never undefined. So these partials are never undefined, so we don't need to worry about that happening. Let's just set them equal to 0 now to find our critical points. So we'll set negative 2x equal to 0. And if I divide by negative 2, we get x equals 0. So let's do the same with the y partial derivative. Let's set 3 minus 3y squared equal to 0. And if we rearrange this, we get that y squared equals 1. And square rooting both sides, we get y equals plus or minus 1. Okay, so at this point we have some critical points, and I'm going to call these points to check. These are possible candidates where the absolute max or the absolute min might happen. So one critical point is when x is 0 and y is 1, and the other one occurs when x is 0 and y is negative 1. But remember that we said that we are just looking for critical points of our function over this domain. And the point 0, negative 1, that is not in this domain. 0, negative 1 would have been somewhere down here. 0, negative 1, and that's clearly outside the domain. So we don't need to bother checking that. But 0, positive 1, that is in the domain. So what I'm going to do is I'm going to start to form a table and keep track of the possible candidates where the max or min might happen. So at this point we have one candidate, which is the point 0, 1. So I'm going to plug those values into the original function. So here's the original function. If I plug in 0 for x and 1 for y, we'll get 2 plus 3, which is 5, minus 1, so 4, and then minus 0, so overall 4. So our function's value is 4 when we plug in 0 for x and 1 for y. Okay, so far we have one possible candidate of where this max or min might happen, this critical point, but we still need to consider the boundary. The max or min might happen at the boundary. So for the boundary, there's sort of two parts to it. There's this line segment here, I'm going to call that part 1, and there's this parabolic sort of portion, and I'm going to call that part 2 of this boundary curve. So I'll consider those one at a time. All right, so what we need to do next is we need to find the extreme points, possible candidates for extreme points on the boundary. So the first part of the boundary that we'll look at is, maybe let's look at the line segment first. So let's look at the line segment from, what are the endpoints of that line segment? So one of the endpoints is negative 3, 0, and the other endpoint is 3, 0. Okay, so we know the equation of this line segment. The equation is y equals 0, but moreover it's y equals 0 with the condition that x is in between negative 3 and positive 3, and it could be equal to either one. That's how we specify that it goes from the endpoint negative 3, 0 to the other endpoint 3, 0. It's just that part of the line. Okay, so on that portion of the boundary curve, y equals 0. So what I can do with that is we can plug that in to our function's formula. Anywhere there's a y, I'm going to plug in 0. Okay, so if we do that, let me zoom it out a little bit more. If we do that, we end up getting that f equals 2 plus 3 times 0 minus 0 cubed minus x squared. So simplifying this, this is 2 minus x squared. So on that boundary curve, on this line segment, our function just equals 2 minus x squared. There's only one variable here now. Okay, so looking at this, our problem on this portion of the boundary becomes a one variable optimization problem. So optimization problem. So recall that optimization just means to maximize or to minimize. So this problem, that's what we're doing. We're trying to optimize this. We're trying to find the max values and the min values. So this is now just a max-min problem from calculus, like we would have seen in a previous calculus class when we were just dealing with functions of one variable. So the way we found max and min points, if we think back, was by doing things like finding critical points. I'm going to take the derivative of f. So the derivative of f would be negative 2x. And that's never undefined, so I'm not going to worry about that. I'm going to set it equal to 0, though. So let's set this equal to 0. And if I divide by negative 2, I get x equals 0. So as a point, if I describe all such points like this, I know the x-coordinate is 0. And I started this process off thinking about this portion of the boundary, this line segment, by saying, oh, y is equal to 0 on that line segment. So my y-coordinate is also 0 here. Okay, so we have our critical point on this portion of the boundary. So now I have some more points to check. We have some more points to check. So one point that I need to check is 0, 0. But if we think back to how we did max-min problems in calculus, finding absolute maxes and absolute mins, not only did we have to look at these critical points, we also had to look at endpoints. So what are the endpoints of this line segment? Well, one endpoint was negative 3, 0, and the other endpoint is 3, 0. So we need to consider those as well. These are the endpoints of the segment. Okay, so I'm going to include these in the table. So in the table, I need to include 0, 0, negative 3, 0, and positive 3, 0. All right, so that was one part of the boundary curve. But now we also have that parabolic portion of the boundary curve to consider. Okay, so let's zoom it in a bit. Let's consider that parabolic portion. So now we got to consider the parabolic curve. Its equation is y equals 9 minus x squared from the point negative 3, 0 to the point 3, 0. So what I'm going to do is I'm going to write down my function's formula, but anywhere there's a y, I'm going to plug in 9 minus x squared. So if we do that, we get 2 plus 3 times y, so 3 times 9 minus x squared, and then it's minus y cubed. So I'll get 9 minus x squared being cubed, and then minus x squared. Okay, so again, this is from looking at my original function. I've got to zoom out quite a bit at this point to look at it. Looking at my original function, and wherever there's a y, I'm plugging in 9 minus x squared. All right. So when we do that, again, this becomes a one variable max-min problem. Okay, so I'm going to first simplify this a bit. I'm going to expand this, combine some like terms, and then we'll take the derivative. Okay, so we get f equals 2 plus 27 minus 3x squared, if we distribute that 3. And then, so I have minus this next part cubed. So to cube this, I could either just multiply it by itself 3 times, or if you know something called the binomial theorem, it gives us a shortcut to figure out what this is. But in any case, this isn't too bad to just cube and work out what it is. If I work out what it is, we get 729 minus 243 x squared plus 27x to the 4th minus x to the 6th. That's what we get if we cube 9 minus x squared and just do a big old FOIL to get it. All right, and then we have that minus x squared at the end. Okay. So now if we combine some like terms, f will be equal to x to the 6th. We'll get a minus 27x to the 4th we'll get plus 239x squared minus 727. So that's what we'll get if we distribute this negative sign into the parentheses terms and then combine like terms. Okay. So we have our function. Let's take the derivative now. So the derivative of this would be 6x to the 5 minus 108x cubed. So this is just doing power rule on a bunch of terms. And then let's bring the 2 down. 2 times 239. That'll give us plus 478x. And the derivative of negative 727 is 0, because that's a constant. Okay, so I got this derivative. It's never going to be undefined. So let's find where it's equal to 0. Okay, so let's set that derivative equal to 0. I can factor an x out of this. And I'm left with 6x to the 4th minus 108x squared plus 478 equals 0. Okay. So this is where it takes kind of like a little bit of a clever step to recognize what algebra trick I can do to deal with this stuff in parentheses. Okay, so this right here is a quadratic in x squared. So what I mean by that is I could express this whole thing, the thing in parentheses, as 6x squared squared, and then minus 108x squared plus 478. So it's kind of a hidden quadratic, but where the variable is x squared instead of just x. So what I'm going to do now is I'm going to do quadratic formula, except instead of writing x equals whatever, like negative b plus or minus square root, I'll write x squared equals negative b plus or minus square root. So that gives me, so from this portion, from this hidden quadratic portion, we'll get x squared is equal to negative b, positive 108, plus or minus square root of b squared, so negative 108 squared, minus 4ac, so a is 6, c is 478, and then all over 2a, so all over 2 times 6. So the other possibility is from this x out in front, we also get that x can be equal to 0, so that part's easy. Okay, so now simplifying this, we end up with 108 plus or minus square root of, so I can use a calculator to work out what this number inside of the square root is. It ends up being 192, and then on the bottom I have 12. So now I need to ask myself, is there anything I can take out of this square root of 192? So it turns out that this square root is equal to the square root of, and 192 is 64 times 3. Okay, so what we have is, we have that 108, plus or minus. If I take the square root of 64, we get 8. And then we have square root of 3 still, and then over 12. Okay, so we can write this as 108 over 12, plus or minus 8 root 3 over 12. So 108 over 12 is 9, and then plus or minus, with the 8 and with the 12, I can cancel a little bit. I can divide both of them by 4, and I'll be left with a 2 on the top and a 3 on the bottom. So I get 2/3. I get 2 root 3 over 3 there. Okay, so we have x either equals 0, or we have x squared equals this 9 plus or minus 2 root 3 over 3. So if I square root both sides, I will end up with, so one possibility is I have 9 plus 2 root 3 over 3, the positive version. I square root it, but when I square root both sides, I have to put a plus or minus. And the other possibility is from the negative version, so 9 minus 2 root 3 over 3. I end up square rooting both sides of that. And again, when I square root both sides, I would get a plus or minus. Okay, so it's looking a little bit complicated. I got roots inside of roots, but this is actually something that we can handle. We can handle without too much more effort. So remember that when we're looking at this parabolic region, that x needs to be between -3 and +3. It can't be outside of that interval from -3 to +3. So we can use that idea to eliminate some of these answers. It turns out that these two values, this positive version of this root, the negative version of this root, lie outside of the interval from -3 to +3, since if I look at 9 plus 2 root 3 over 3, well, I want to get a sense for how big the square root of this thing is. And 9 plus something, this is greater than 9. So if I square root both sides of this, we get that the square root of 9 plus 2 root 3 over 3 is going to be greater than the square root of 9, which is 3. So that means the square root of 9 plus 2 root 3 over 3 is a number that's larger than 3. So the positive and the negative version of that thing are definitely going to be outside of -3 to 3, this interval. Okay, so as a result, we get to ignore this value. All right, so nonetheless, what I need to do now is for these x values that I do have, I got to find their y values. So first off, for x equals 0, I can get the y value by remembering that these are points on the parabola. So that was y equals 9 minus x squared. In this case, I'll get 9 minus 0 squared. So I'm plugging 0 in to the equation of my parabola, 9 minus x squared. In this case, 9 minus 0 squared. And that's 9. Okay, so I have another point to check. It is 0, 9. So 0, 9. Okay, and then we also got to plug in the plus or minus root that did work, 9 minus 2 root 3 over 3. So this one, the 9 minus 2 root 3 over 3 was okay, because if we do 9 minus that fraction, it's going to be less than 9. And the square root of something that's less than 9 is going to be inside of the interval from -3 to +3. Okay, so if we take these x values and I plug them into my parabola equation, we'll get y equals 9 minus this thing squared. So this either positive or negative, this square root squared. So when we square that thing, it's going to cancel the square root. And then the 9 in front will cancel this 9 inside. And we'll actually end up with just the positive version of that fractional term. So you should check that. I kind of did a few steps at once there, but you should check. It's pretty quick to check that we end up with 2 root 3 over 3. Okay, so I'm going to just write down my points to check. I kind of jumped ahead a little bit. I put one of them in the table already. The one that I already put in the table was 0, 9. Now I know that I also have my x value could be plus or minus square root of 9 minus 2 root 3 over 3. And when that's my x value, my y value is 2 root 3 over 3. Okay, so those are sort of the critical values that I was getting for this parabolic curve. But we also got to do the endpoints. The endpoints of the parabolic curve are a -3, 0 and +3, 0. We got to always include the endpoints when we do the boundary, whatever portion of the boundary we're looking at, endpoints. Okay, so let's add these points to the table. Well, I already put 0, 9. Okay, so let's do the next one with the square roots. So we could have x as the positive square root of 9 minus 2 root 3 over 3. Or it could be the negative root 9 minus 2 root 3 over 3. And the y value for both of them was 2 root 3 over 3. And this one also 2 root 3 over 3. And these other endpoints, -3, 0, we got. And 3, 0, we got that one as well. Remember, we got those. We had already listed those as being the endpoints of the line segment. The endpoints of the line segment just so happened to be the endpoints of the parabolic curve as well. Okay, so we have a complete list of possibilities where the absolute max and the absolute min might happen. I just got to plug all of these into the original function now. So here was the original function, f of x comma y equals 2 plus 3y minus y cubed minus x squared. Okay, so if we plug these in, I'm just going to tell you what we get. So if we plug in 0, 0, we'll end up getting 2. If we plug in 3, 0 or negative 3, 0, both of them we get negative 7. If we plug in 0, 9, we get negative 700. And when you plug in these other two values, we'll get the same thing for both. We'll get 16 root 3 over 9 minus 7. Same thing here, 16 root 3 over 9 minus 7. And plugging those ones into a calculator to estimate what they are, we get that these are approximately equal to negative 3.92. So we see now that the absolute max is 4. This is the largest output that we got. And the absolute min is negative 700. That is our absolute min. Okay, so I just got to write down a sentence of conclusion now. So we would say that the absolute max value is 4, which occurs at the point 0, 1. And the absolute min value is negative 700. So when a question asks for the absolute max value and the absolute min value, ultimately it wants the output as the answer. So that's what I'm listing here, the outputs. Okay, and let's write down where this happens. So the absolute min occurs at the point 0, 9. And that's my answer. Alrighty, so in terms of our goals, we've now talked about how we can find the absolute mins and maxes of a multivariable function on a closed and bounded region. So we really looked at a pretty challenging example in this question. We had to take some partial derivatives and do some more sophisticated algebra to actually handle this.